LaTeX package that I've developed. It allows you to put Python code in your LaTeX documents, execute the code, bring the results back into the documents. And when we're talking about ways that you can use that to create reproducible documents. We've heard a lot about makefile style reproducibility over the last few days. And in that sort of a workflow, you might create your paper, all the figures, all the results with a makefile or something similar to that. The approach that I'm going to be referring to a bit more, though, is where you actually have code embedded in the document itself, and that's going back to roots in literate programming. Sweave is maybe one of the better-known examples of this approach, where we have R and LaTeX combined. There's also knitr, which is a more recent and advanced version of that. And then in the Python ecosystem, probably IPython's the best known thing that we have for combining text and code, having the two interact. There's also SageTeX, SimpyTeX, pweave, some other options. And then what I'm doing with PythonTeX is building on some of the previous LaTeX solutions, especially SageTeX, and really emphasizing close LaTeX integration, a lot of usability and performance features. In terms of getting started with PythonTeX, very simple. You just install. It's on C10. It's also on GitHub. At the beginning of your document, you do the standard utes package. And then in terms of actually compiling documents, you do it just a little bit different than the standard workflow if you have any new Python code. If you've just edited the LaTeX part of the document, just compile it like you normally would. But if you do change the Python code that's involved, there's a 3-step compile process. This gets the Python code out of the document, runs the code, and then brings it back in again. Before I really get into the main part of the talk, just a very quick example of what using PythonTeX in a document looks like. So at the top there, I have an example of some LaTeX code. Down at the bottom is the output. And in the first environment there, the Py code, everything in that gets executed. I have an import from future. The code that you put in as the user, it actually gets put into a template before it's executed. But I have code that goes through the beginning of anything that you'll enter, finds any future imports, relocates those in the template, and that it still all will execute correctly. Then I'm defining a number and printing that number, and whatever you print within the document or print within the PyCode environment, it goes straight into the document, and so that's giving us the 2.23 down there at the top of the output. There's also an inline command, pyc, short for PyCode, just the equivalent of the PyCode environment if you just need to do something really short and simple, and that's giving us the 50.17 in the output. And in a lot of cases, you just want to access the value of some particular variable. You don't want to have to worry about actually typing in the whole print. So I've also got a py command that just takes whatever you give it, gives you a string representation of that, and that's giving us the 2.23 down there at the bottom. You can customize exactly how the string formatting works, and I'm not going to get into a lot of the other commands and environments that the package creates, but you'll see there the SciPy example. There's a SciPy command, and you can do some really nice symbolic math using SciPy's built-in conversion of equations into LaTeX, the pi cosine 2 down there, all the formatting to get the pi and so forth, automatically done by SciPy's built-in LaTeX printer. So that's sort of what the using the package in your document can look like. And what I'm going to do now for most of the remainder of my time is look at just sort of a simple toy analysis case just to illustrate some of the different features of the package that can help your documents be a bit more reproducible. I'm going to be looking at a very simple data set. This is just a random walk. So we start at 0, 50-50 odds, +1, -1 step, go 100 steps. And I'm just going to calculate the average distance and the maximum distance traveled from 0 from the origin, and then also plot the walk. So I'm going to use the same PyCode environment. At the top there, I'm just reading in the data set. I don't even have to use any special imports in this case, just use the max, sum, and len functions. And then after the end of the PyCode environment, I'm referring back to the variables that I had defined earlier using the py command. And one of the really nice things about this is I don't have to go back and copy some numerical values into my paper. That's automatically pulled straight from the code. So that just reduces one potential source for error. In terms of the plotting, we could again use the PyCode environment. Now, one of the additional features that I do have with the package is the possibility to have user-defined sessions. And so you'll notice here after the PyCode environment starts, there's the line that says in the square brackets plot session. So I'm naming a custom Python session. All of this code will run in that session, and all sessions automatically run in parallel. So if you're making a lot of plots, you can just put each plot in its own session as long as they're independent. Those will all run in parallel. And if you have several cores on your machine, which I usually work with at least quad-core machines, that can really speed up the creation of your documents. So we go through standard plotting with this, get something like this, then back in the document. And the advantage of having the Python code for the plotting embedded in the document is that if you're working with your document and you decide maybe we shouldn't have had that be blue, we should have had that be red, or maybe we want dashed lines instead, all you'll have to do is, if you've got your tech editor set up with forward and inverse search, you can just double click on your plot there, jump right back to your LaTeX code, edit the relevant part to change the color or whatever else you want to change, rerun the LaTeX, PythonTeX, LaTeX again, and your plot will automatically be updated. So short circuit some of the potential for editing, slowing things down. Now, all of that is assuming that nothing goes wrong in the process. And when things do go wrong with this combination of Python inside of LaTeX, you can imagine that that could get a little bit complicated. So in this particular case, I'm just copying the code I had previously to calculate the averages and maximum. And then I switched the max. I took out the A, so I have a misspelled function name. And the output in that case, we're not going to have LaTeX is going to be able to finish, but it's going to give warnings because it couldn't find the Python-generated output. And then we're going to have warnings. So in the output, then those question mark placeholders will appear in the document. But the really useful part for debugging is that when the PythonTeX program runs, your output will look something like what I have here. And what that's giving us is the raw standard error coming out of the temporary script that was executed. In this case, the temporary script was PyDefault. And then interspersed with that, there's the line that starts with the asterisk. And that's telling us where in the document the error occurred. So we just scroll back to line 157 in the document. That's where the error happened. We can go ahead and fix it. Now, there are cases where the standard error will not refer to a particular line in the user plus template code. Warnings.warn will typically just refer to the actual file in which it's executed, but even in those cases, I can always track the location back to a single command or environment, because as all of this runs, I'm writing delimiters into standard error, and I can use those delimiters to always trace things back to a single command or environment. So debugging, usually very simple. There's also, as I'm showing here at the very end, a summary of the number of errors and warnings. So if you do get a lot of these, you can very quickly just glance at the summary and know what you're dealing with. One thing that you do have to decide if there are any errors in the Python code or if there are warnings is how you want to deal with those in subsequent runs. In some cases, if you're bringing in some sort of external file into your Python and that's causing the problem, maybe you just need to go to that file, tweak it, and you want to rerun the code the next time. On the other hand, if the error is being caused by something like I had here, syntax error, I'm trying to refer to some function that doesn't even exist, so I'm using the wrong name, then you might not want to rerun the code unless you've gone back and fixed that and modified it. So I have a package option called rerun, and there are a number of thresholds that you can set with that to determine when the code's going to be executed again. You can turn off execution. You can always execute the code. You can execute it if it's just been modified based on the errors and warnings and so forth. Typically, since everything that the Python produces is cached, you don't need to rerun it always. But if you ever had really time-sensitive information, if you were like pulling something off the web or something like that, you could certainly set it up to use the always option. So that takes care of one thing that could go wrong in terms of the errors and warnings. Another thing that could get a little bit tricky is if the actual data file that I read in was modified, because as things stand right now, the PythonTeX program, when it runs, it doesn't know anything about that data file. Now, all the user code that you put into the document, it's put into a template, and in that template, The PythonTeX utilities class, which I've created, is automatically imported, and you get an instance of that utilities class, and that provides a TeX-Python interface. You can manage a lot of things through that, but the thing that's relevant in this case is that there's an add dependencies method, and so you can specify with that the external files that you're bringing in. So if I was to go back to the previous code, add something like this, where there's a PyTeX add dependencies, the name of the data file. After this, PythonTeX knows about the existence of that file, and so anytime that it detects either the hash or the modification time changing, whichever one you want to specify, it's going to rerun all the code, and you'll automatically get everything updated. One thing that you could do to really automate this whole process is just define your own custom version of open that automatically, whatever you give it, it's going to add it as a dependency if you open something for reading. And this way you can actually have all this dependency tracking going on behind the scenes. You never have to actually consciously worry about it once you've configured things. One of the disadvantages with this approach that I realized relatively early on is that if we have these LaTeX documents with all of this Python code in the document with all those custom commands like the PyCode environment, the PyC command, and so forth, that's something that most journals are not going to be real happy about. And then also you have programs like Pandoc that will do conversion for you, but that's going to break down because they don't know about these custom commands. So I've created a dPythonTeX utility. This creates a copy of your document. All the Python-generated content has been substituted in, and there's a lot of control over how any highlighted typeset code's handled. You can just have it be plain verbatim. You can have it be still syntax highlighted. You can actually take the code that's highlighted with PythonTeX and maintain your line numbering during the conversion process. So typically what you'll get out of dPythonTeX is a perfect, I try to have it be perfect to the actual space, to the line breaks, copy of what you originally had. Now, if you do change the way that you typeset code, things might be just a tiny bit different, but I try to have it be extremely close to the original case. In any case, the output that you get, good for conversion with Pandoc, journal submission, anything else that you would typically do with your document. And just to give you a very quick example of what this can look like, I have a gallery file on GitHub. I create this just as a PythonTeX document, but I have a little Python script that I tweak a few things in the document to make it compatible with Pandoc. Then I run Pandoc on this. And this HTML file here, all of this was originally written in LaTeX with PythonTeX, then converted with Pandoc. All the equations in here are with MathJax. Got a plot from matplotlib. A lot of automatically generated derivatives and integrals. Also, well, that was through SciPy. Some step-by-step solutions with SciPy, and some additional examples. So all of that in HTML, straight off of the PDF source, and I just had to do a tiny bit of pre-processing on that to get it to work with Pandoc, send it through Pandoc, very nice output. So Pandoc doesn't support LaTeX figure environments, and a couple other really special things that I did in my gallery document. And so I wrote a Python script that just takes out the begin figure, end figure, the PythonTeX program. The program is allowing you to run the code and get the output back in the document. The HTML that I just showed is if you take a document, the PDF that, well, you can take the text source that you would use to normally make the PDF, and you can run that through the Pandoc converter and then get an HTML file at the end. Well, basically, Pandoc will convert a lot of LaTeX, but not everything. So I just had to tweak the file a little bit with Python before I sent it through Pandoc, and then I was able to get the full conversion. Yeah. So to wrap things up, I think I'm about out of time. I am just recently in the process of adding support for additional languages. Typically, you can add support for another language, maybe 100 lines of code or so if you're going to have full support. If you just want really, really basic access, you can get by with less than that. And just added Ruby support. So example here, I actually, when I compiled the slides, did run a Ruby process, got the Ruby output back in the slide here, and I have Julia support probably ready to go as soon as they come out with their next release of binaries, and I'll be adding support for some additional languages over the rest of the summer and the fall. So in conclusion, future directions, got some additional debugging and fine-tuning features coming. We'll be working on better support for macro programming. You can actually create macros like I've got right there, say for finding powers that mix LaTeX and Python. But PythonTeX doesn't quite support that yet in terms of replacing those macros with the output. And one thing that I've thought about just a little bit, and I'd be interested in talking with any of the rest of you over the next couple of days, I'll be around till Saturday, is whether an alternate interface to some of the PythonTeX internals that would work with, say, Markdown or restructured text might be something to think about in the future. So I'll stop there and be happy to take questions. Thank you. Okay. Yes.
Do you have an option so that the code doesn't display in the final logic document? And whether you can choose that this block of code display and this one not display?
So I didn't go through the question was if the code can be displayed or not in the final output. And I have different commands and environments for if you want to just execute code, which with the PyCode things that I was showing. There's another set called PyBlock that if you want to execute and typeset. And there's another set, verbatim ones, if you just want to typeset. So you've got all possible combinations of showing the code with highlighting and executing. Yeah. Yes. So the question is, what's the difference between my package and Python? The Python.sty, let's see, the Python.sty package, yes. That just takes whatever you give it in the environment, it writes it to a temporary file, it executes it, brings it right back in. And with what I have, you don't have the option to save all your, well, with what I've got, you can keep accessing all your variables between commands and environments. You can't do that with the just plain Python package. You don't have the multiprocessing and the syntax highlighting and all that kind of thing. Yeah. Yes, in the back. Mm-hmm. Mm-hmm. So the question is about how documents that include other documents work with the package and potential issues with that. That's certainly something I'm aware of, that if you have documents that you're bringing in that are also using the package, things can get a little bit tricky with that, and that's definitely on the list of things to work on. Unfortunately, in those cases, some of these things get tricky, and some of the synchronizing of the error origins and things like that can get tricky, but I'm hoping to fix some of that at some point. Yeah.
So, I mean, this is my first time looking at this library, but
Mm-hmm.
I just use LaTeX, just the text file. This seems to me that it's a really good way of reproducing some experiment that you had and doing it in a Python file, right? And then putting that into the outputs and the code. Yeah. But could you actually use this to actually generate, instead of using the LaTeX file, you could actually just publish with this? You understand my question?
Not quite sure if I'm completely.
Could you, if I
Mhm.
30-page paper. And I was just going to use the regular LaTeX way of doing it.
Mhm.
Could you do it for this, or is this more just for, getting Python code and its output?
This, okay, I understand the question. So the question is whether you would use this basically just for showing the code, or if you could also use it for standard writing. You can do it for either one, and my primary objective getting started on this was to basically, instead of writing your paper and then you have to edit a figure, you have to stop working your text editor, you switch over, you find the script that you use to create the figure, change things. The idea is everything's just in a single file in terms of figures and text, and so it just keeps everything in a single location, faster to work with. But in terms of your final output, whether you're writing about code, whether you're doing a scientific paper, it doesn't make any difference.